Okay, shall we start then? Today we have with us here Dr. Juan Carlos Suárez from Granada University, but he has been here at the IAA for a long time, actually being my office mate, which I don't know if I'm happy about that or I regret it. Simply, I don't know. No, I think he was a very good office mate. He did his PhD in Paris Melon. He finished in 2002, 2003, 2002. And just after that, he got a contract here at the Institute, and he came at that time here at the Instituto Astrofísica, where we started to share a very small office in the main building. And then, well, he did some postdoctoral positions, postdoctoral stays abroad, and he got his Ramon Cajal in 2014, and he went to the university here in Granada, position that he has been holding since, and now he's going to talk to us about Plato. A mission recently selected by ESA to be a M5. It's now the it's the M3. Yeah, M3 mission of ESA, and of which he is responsible in Granada, at least at the university. And also we have here a group at the physical department. Stellar physics department working also on this project, so we are very much involved in this mission, which hopefully goes very well. Thanks, Juan Carlos. You can give you the floor now.
I have to say two things. It is true that we were mates in a long time ago. Yeah, I think in the most tight room in the institute. I have to say. Well, this is a personal charm, yeah. And also, I would like to stress that I'm also associate doctor here in the institute since, well, 1 year ago, more or less. Well, I was wondering if speaking in English or Spanish, but I guess that since the introduction was in English, it's because there are in the audience people that prefer to listen in English. So, well, just for starting, there's a little mixture between Spanish and English. The title is From Hunting to Domesticate Planetary Systems. Why this title? Because up to now, we can see this race of space missions, most of them already flying. You can maybe recognize most of them, principally Gaia, because probably most of you work with Gaia data. But related to the topic I will speak today, which is the detection of planets and characterization of planets, there are some of them which are very interesting and really focused on this, which are the Corot mission, really the first big one. It is a French mission. French-European mission with a significant participation of Spain here, in particularly from the Granada team here from the Institute. The NASA mission Kepler, now the name is K2 because the original mission is over, and then they are just taking advantages of some data that the mission can still give. And this is a quite wide field mission, but focused on just one place of the space, let's say. And thanks to Kepler, maybe you have heard about the discovery of hundreds and even thousands of exoplanetary systems. This was launched in 2009. And since that, we have been gathering data, very valuable data, not only for planetary science, but also for stellar science. I will speak about this afterwards. Then in between there is the Gaia data. Now we have the second release of the Gaia data, which is very, very, very useful for any kind of science we can imagine with stars and even with other kind of science, astrophysical science. And for particularly for us, for planetary and stellar science is quite important because it gives us distances and even photometric calibrations and so on, that it is very valuable for us. So we are now, if we can see the literature now, we see that there are coming papers with the connection between astroseismology, for instance, and Gaia data, and the increasing of precision is growing. Then recently there is the test mission, which is another American mission that has just been launched some weeks ago. So it is in commissioning phase. And well, this mission will cover more field in the sky than the Kepler mission, with even more precision. So we will see up to which kind of planets the test mission will be able to detect and maybe characterize. And the future will be this James Webb Telescope. The idea is that Kepler, well, Corot, Kepler, TESS, and Plato will provide targets for missions that are focusing on studying atmospheres of planets detected with the previous missions, right? Well, I forgot CUBE's missions, which is a short mission. It should be launched this year, but there are some delays. It will be launched very soon. Well, this is the context, the space mission context in which Plato is well addressed. The point of the arrow is where Plato goes. Plato will be launched in 2026. So we are just working on it. Oh, yes. Well, a little bit of history of the Plato mission. Plato mission was conceived a long time ago, around 2005 or so, where another ESA mission was dropped. But the consortium, let's say, just keep discussing about a new strategy, a new kind of mission, with more challenges to address, and we came up with Plato. Plato, that means planetary transits and oscillations of stars. And in 2011, we present our candidature for M1, M2 ESA missions. Unfortunately, we didn't pass the final stage. We arrived to the final stage, but we didn't pass it. But the commission, the evaluation commission of ESA Evaluation Commission, told us to present in the next one because they saw that the architecture, the project, and the feasibility of the project, and the interest, the scientific objective of the project was so important that they would like to see it again in the next revision. And the next revision was in M3 in 2014, where finally we were selected by ESA, and we start to work. This was the year I was selected also for a Ramon y Cajal contract, so I was very happy everywhere. So, well, this is a little bit a summary of the scheduling foreseen for the Plato mission. In 2016, we passed some reviews, the system requirement review, the SRR, and the adoption of the mission. The adoption of the mission is important, is the time where ESA is, let's say, more comfortable with everything. At the beginning is comfortable only with the scientific projects, and the idea is very good, I think it's feasible, but you have to demonstrate it in a couple of years that the budget it will not increase or double, or everything at the end is not possible. So with the SRR passed successfully, finally the adoption came with some problem in the ESA budget and so on. So we have some reduction in the scientific objectives, a little bit. I will tell you about that in the next slides. Then PDR, instrument and mission PDR was passed in 2017. It is foreseen that the flight model integration will come in 2022. Well, all these dates are changing a little bit in every meeting we have. So maybe I am wrong in 1 or 2 years in some of the dates, in particular for this. But for the launch, by now it is for sure that it will be in the Q4 of 2026. So it had been a delay of 2 years, I think, from the initial previsions. I mentioned here OHB because just recently, I think 1 week ago, it was announced that the prime of the mission will be OHB. Okay, this is a company OHB, a private company OHB, in combination with other companies like Thales, Alenia, that will be the prime of the mission. So this is another important point, another important step in the development of missions, because once we have the prime, the problems arrive. And so the engineers are not very happy, but it is the this is another word that our project manager told me in a couple of days ago. That means, co-engineering means that we have to share our developments, our designing and so on with engineers from ESA and from the prime. Right. So sometimes this is not an easy task. Well, I said at the beginning that Plato is more than another planet hunter. Of course, Plato will hunt some new planets, hopefully. But the main idea of Plato is not only to detect them, but to characterize them. Characterize them with sufficient accuracy, precision, to do the next step in science, which is not only, let's say, to make statistics about the type of planet that we find, the distance to the stars, the period of those planets, and so on, but also tell about, for example, the physics of the interiors of those planets. And for this, we need a very high precision. And this is the main objective of Plato. Addressing questions like how do planets and planetary systems form and evolve? Is the solar system unique, or is life unique? For all the missions, these questions are there always, but Plato will be in a good position to really address some of them. Yeah, to do that, we need to characterize Earth-like planets in the region of the space that we call the habitable zone. This is the region in which water can be found in the liquid state. This is the basic definition of a habitable zone. There are more definitions, more complicated and more, but the basic one is this. So Plato will characterize Earth-like planets in the habitable zone of solar-like stars. That is to find other solar systems, let's say. And it will do it for a large sample of stars, for which it is important to have the well-determined, with high accuracy and precision, their stellar parameters. That is, we need ground-based observations for this, because even with very nice Gaia data or photometric data, the physical parameters of stars are still given by high resolution spectroscopy from ground. And at the end, we'll provide input for improved stellar models. We need stellar models, of course, in order to characterize the system. The systems, the planetary systems, in fact, are the combination of two important parts, the planets and the star. If we know very well the star, we will know with high precision and accuracy the physical parameters of the planets. Otherwise, it's impossible. Well, how do we do it? With the main way of detecting planets are a combination. Well, there is a combination of three methodologies. One is the planetary transits, the radial velocities measurements. Here, what you can see in this plot, well, it is a little bit outdated, but in any case, it has not changed too much. This is the size relative to the Earth as a function of the orbital periods in days. These are the candidates, or these were the candidates at some point. Most of them are still candidates because it's very difficult to pass from candidate to actual planets. It depends on very precise measurements, radial velocity measurements at the end from the ground. And it's not very easy to find time for observing all those planets, taking into account the depression that we have in 3-4 meters telescopes. So from radial velocity surveys, what we have here is that planet mass relative to the Earth concentrate in this region between 1 and 3. So with the Kepler missions and radial velocity surveys from 2009 up to now, so we have seen that the most frequent planets are those which are small and light, right? So for the detected and confirmed planets, what we can see here is in this plot which confronts the stellar mass with the semi-major axis. This is the distance to the star. And this green region is the habitable zone. So we can see that Venus, Earth are exactly inside the habitable zone, and Mars is just at the edge. And the present status well, is that a few small light planets in the habitable zone are detected. All of this. The rest of them are there, right? But one thing is we have detected those planets in this region, and the other thing is to characterize them with a precise radius and mass. And this is only happens really for a really few of them, almost none of them, right? Well, in the context of Plato, I showed you before the other missions like TESS, KEOPS, K2. TESS, KEOPS, and K2 will cover this range, right? That is planets with periods up to 80 days. This is the region that will be covered by those missions. And Plato hopefully will cover all the diagram. So this is the importance of Plato. This will be a big mission in the sense of the scientific objectives that we'll address. In order to fill this diagram with in red I showed you before, we need precision in the determination of mass, radii, and ages of 10%, 2% in the radius, and about 10% in ages. Right? This is something that is very hard to achieve. We are arriving to this precision. We have demonstrated with the Kepler data and radial velocity measurements from the ground that we are able to achieve this kind of objectives. And to do this, as I said before, we will combine different methods. Photometric transits, as you can see here, Okay, this is a comparison with a light curve with no transits and a light curve with a transit, as you can see. These methods of transit will give us radii with a precision of 2%. Radial velocity measurements with the follow-ups in particular. We need a follow-up of these observations, not just a shot, but really a follow-up because we need time series. We can get a mass of masses of 1%. And well, this is what we say in every conference. Of course, then the reality will come us and will show us that maybe it's not so low, but of the order I said before. And but this is the objective, and we are working on this to achieve this objective. And ages from astroseismology. In fact, astroseismology can also give radii and masses with a very high precision, but it depends mainly on astroseismic models, and it will probably be useful to compare the results from photometric transits and radial velocities follow-up. And but the main point of astroseismology is to get ages up to 10% in precision. Well, all this will be achieved for a sample of all the stars that will be observed by Plato, which will be mainly the brightest one, between 4 and 11 magnitudes. This is the main sample. Solar-like stars, bright solar-like stars with planetary systems around. But the detection limit will be around 13 magnitudes for terrestrial planet detection, right? But it can achieve, even arrive to 16 magnitudes for other kind of science, for other type of stars. Well, as I said, Corot and Kepler have demonstrated that we are able to achieve this. So this was one of the key points that allow us to be selected in 2014, because we show it with legacy data from those missions. So here we can see the uncertainties without including seismic measurements. These uncertainties are of around 25%. It's ridiculous. So we know the age or no? We have no idea of the age. This is the measure, the message. But with astroseismic measurements, we'll have a very accurate determination of ages, around 13%, right? Well, this is a typical oscillation spectrum of a solar type star, as you can see here, only from 4 months of data. Kepler has followed some of the targets for 4 years or even more in some of the cases. Plato, unfortunately, with the last revisions from ESA and budget cuts and so on, will not allow us to follow so long a star. At the beginning, that was the idea, at least 4 years or even 6. But finally, the long observations will be at most of 2 years. But in any case, it is not a problem to achieve the goals. Well, this is a scheme that we generally show in our talks to show you that currently the uncertainties in the determination of radii and masses prevent us really to differentiate the physics in the planetary interiors. Here you can see these 3 lines are for different type of planets with the inner core made of iron, silicates of ice. This is an example. There are more. This is an example. With those error bars, it's impossible to disentangle between these lines. But with Plato, with an error bar of the size of this box, the red one, this will be possible, clearly possible, to disentangle between the different kind of planets and the origin of those planets. Well, in fact, Plato, for the first time, will provide accurate ages, very accurate ages, as I said before, if everything goes well, with 10%. And this will make possible to do a lot of kind of science, not only the planetary science we are focusing on, but a lot of science related to planets, related to life, even related to stellar physics. To do this, we have to combine very precise, ultra precise, I would say, photometric data, time series, that is long-term photometry. This is Plato. Plato will do the job. We have things we have to cover most of the sky, and in some part of the sky, there will be a lot of, let's say, contamination of stars that are not in different fields and different distances. We will use the Gaia data for such a decontamination of the stars in the PCF of Plato. So in the PCF of Plato, we will have our target stars, but also other stars which are not our targets and will contaminate our sample. And thanks to Gaia, we will decontaminate it. And finally, we need, this is a very important part of the project, is the follow-up. It's very important for Plato, but it has been very important for Kepler, and it was very important for Corot. We really need ground-based observations for two things, in order to have the fundamental parameters of stars with very high precision, but also radial velocities for first to confirm the planetary transits, and then to provide additional information for the astroseismic studies. And this is where Kamenis can be a very key point. It can play a very important role in this. The discussions between the Kamenis team and the Plato teams started from the beginning. It is very clear that Kamenis will be useful, or could be useful, for the ground-based follow-up of Plato, and we are working on this. In 2026, the main, let's say, scientific case of Kamenis is over, and there is no problem to use this instrument for the follow-up of Plato. Well, Plato will cover 50% of the sky in the core program. The core program passed from, at the beginning, was 6 years plus 2 or 3, depending. But due to the budget cuts in ESA, now it is of 4 years. It's a nominal observation period in which we will observe the half of the sky. Hopefully, with the remaining 3 years of the science operations, if everything goes well, we will cover the 85 or 90% of the sky. So these are the fields of the Plato mission. This is an example, an illustration of the fields of Plato. And for comparison, I just give you an idea, an overview of the Kepler field of view here in yellow, and the small blue ones are the Corot field of view. So you can see, well, TESS, in fact, is around 400 times, I think, Kepler. So, yeah, I forgot to put it TESS, but probably TESS is the size of one of these green, but even lower than Plato. Well, this scheme just relates the different kind of pointings and the type of stars involved and so on. The main point to retain here is that the exoplanet characterization and astroseismology will be done for a core program that will observe to 20,000 stars. Okay, that is, for those stars we will achieve the precision, the photometric precision required to do the main objectives of the mission. Then, for stars up to 16 magnitudes, that will be around 5,000 stars, we'll have N-dwarf and host star sample 2 that will be added to the scientific mission, and the P5 for the remaining almost 300,000 stars, which we will provide exoplanet statistics and stellar science. At the end of the mission, including the main operation time and the extension, we will observe around 1 million stars. Well, this is the distribution of transiting systems observed by Kepler and others. As you can see, the stars that are affected are, for Kepler, between 10 and 16. This is by construction because Kepler was designed for this, in order to see just in one field, but in a very crowded field. And to have a very crowded field, we have to lower our magnitudes. And this is why Kepler worked between 10 and 18 magnitudes. And other missions, here it can be included Corot. Corot was able to observe very bright stars between 4 and 6. Normally it was between 6 and 8. Right? But Plato will cover this part of the diagram, right? We'll cover between 7 up to 16. So it will be a mixture between the results from one and another, with much more stars and much more precision. Well, the follow-up expected of the expected planetary yield from the core sample is this. Normally, with telescopes of 1 meter up to 4 meter telescopes will be enough to do this follow-up. This is why Carmenes in Calar Alto could be a perfect instrument to do this follow-up. Only in the hardest cases, as I mentioned here, that is very faint objects with very small and light planets, down to Earth masses, Earth sizes, and even lower than that, we will need something bigger, that is the ELT. Well, this diagram is the result of some kind of modeling with taking into account the current data, the current detection, and the current statistics between the radius of the planets and the distance to the star. The main point to consider here is that Plato will observe more than 2,000 super-Earths. Super-Earths are planets with the size of the Earth, but a little bit higher and a little bit more massive, right? And from those, 300 will be fully characterized. Fully characterized in the sense of determining with very high precision the mass, radius, and ages, including the planets in the habitable zone. And in addition to this, we will observe and we will detect thousands of other planets. That will be a very interesting data for the legacy of the Plato mission. Well, as a summary of the objectives of the mission is that Plato will provide thousands of well-characterized planets of all types. It will characterize Earth-sized planets, Earth-sized Neptune planets in the habitable zone of solar-like stars. That is, we will find other solar systems, and will compile a large catalog of bright targets. Not only for atmosphere spectroscopic follow-up studies, but also it will be a key information for stellar science. And at the end, the main message that we want to give you is that we will be able to finally do comparative planetology. As I mentioned in the plot before, we will be able to disentangle, to distinguish between different planets with different inner cores and so on. So this is the key of the Plato mission. Well, what time is it? Because I start to speak and you do 35, 15 minutes is okay? Oh, well. Okay, the mission. What is Plato? Plato is this. It's a bunch of small telescopes, as you can see here. Instead of a single one, instead of a single reflector one like TESS, Corot, Kepler and so on, is a bunch of them. Why? Because at the same time we wanted to observe bright stars and have a field. And this can be only achieved if we have this kind of architecture. Small refractory telescopes all together in order to be able to observe bright stars and a wide field at the same time. And this is an example of what we will have. This will be an overlap of the different telescopes in order to increase the field of view. As you can see, from here to there is 48.5 degrees, which is a lot. Well, this scheme was prepared for when we had 32 cameras. Now we have 26, but the idea is similar. Well, as I mentioned at the beginning, the prime has just been selected, and the first thing that the prime just sent to us was the new image of the telescope. So now is a kind of Darth Vader, you know, head. But well, the idea is there. It's still all these small telescopes all together in this. It's not very nice to show it, but if it works, then the science will be very important. Well, it will be launched in 2026. As I said, the operation, the main operations will be for 4 years, with a probably extension of 3 years. We'll have a set of 26 telescopes, 24 of them what we call normal telescopes, and 2 fast cameras. The idea of having fast cameras is for providing additional information for calibration, and also for science that we need, and that increase the statistics and the precision that we need for transit analysis, but also for astroseismology. And this, well, we'll have long pointings, well, at about 2 years, maybe 1-2 years, and then what we call step and stair phase, in which we change the field of view each 2 or 3 months. And this is for depending on the science case that we want to address. At the end, we will observe 1 million stars, and in a band, in a range of magnitudes between 4 and 13. Well, this is what looks like the telescopes. It seems small, but they are quite heavy. There will be 24 of this, well, 26 in fact, that will weigh 12 kilos each. And this is a little video of how the optics elements are built, and this is an example, an illustration of those telescopes, those cameras PSF. It's a quite complicated PSF, but engineers have demonstrated the feasibility to use them for science. Well, this is the typical tree scheme of ESA missions. It's quite boring, so I'm not going to enter into detail. Just to mention that Spain is here in the Plato Mission Consortium with 2 people, Miguel Mas and myself. Miguel Mas from the CAP and myself from Universidad de Granada and Instituto de Astrofísica Andalucía. And we have our flags here in 2 more systems. The focal plane assembly that it is being done, it is being worked on in the CAP, in the INTA, and the main electronic units that are being designed and constructed here in the audit, in the institute. Apart from this, we will work in the calibration of the cameras that will be done in Madrid, also in INTA. Well, how the Spanish contribution is coordinated? Well, we are coordinated, we are split in 5 institutes, INTA, CAP, Universidad de Granada, Instituto de Astrofísica de Andalucía, and Instituto de Astrofísica de Canarias. The coordination is held by Miguel Mas and David Barrado from the CAP. And, well, these are the different systems. The focal plane assembly is done here in the INTA. The main electronic units and the operation of Nomad are funded for the project here in Granada. And the power supply unit is being designed and constructed in the IAC. Well, I have to say that this is a subsystem that it depends directly on the Granada MEU. Well, in addition to the hardware, this is what I have just shown. There are a lot of people working in the mission in Spain, in the different institutes, through the work packages. There are plenty of work packages in the Plato Data Center. PDC is Plato Data Center. That is the people who is working in the preparing the pipelines that will analyze the data, and in science and follow-up. So as you can see, there are, well, I am coordinating 2 work packages. Antonio Claret also is coordinated another one. There are a lot of people from this institute and Granada and IAC and other part of Spain that is working hard and coordinating, not only working and just participating, but coordinating those packages. I just mentioned that. Well, just 2 words about the focal plane assembly. The focal plane assembly is the part of the instrument that will assemble the camera, join the camera with the rest of the instrument. So this is this part. Here will be installed the CCD cameras, and all the, let's say, the electronics and mechanics related to this connection is being developed in INTA. This is a view from above of this subsystem, and this is from below. In total, there will be 4 CCDs for a focal plane, so we will have to treat around 81 megapixels each 25 seconds of observation per telescope. So this means that we will have to deal with 2,100 megapixels in total. Well, this is a prototype made by Lidax, which is the company working with CAP to develop this. And if I'm not wrong, it is made by titanium. And regarding the processing, which is the main hardware work here in the institute, we will observe for the main core of the main core, and then the next one 102,000 and 20,000 stars. We will deal with 1.2 million bits per second. We have to process all this kind of information. I mean, every 25 seconds, there is a unit made here in the Institute, what we'll call the MEU, that will have to process all this kind of information that will arrive to with this velocity. The processing of this data means the extraction. The extraction. Oh, sorry. Yeah. The extraction of the photometric data, the recentering, because the telescopes is moving a little bit, so we need to the own data, the proper data of the mission to recentering the fields, reduction of the cosmic rays, calibration and extraction of the light curves, and so on. All this is done in what we call the onboard data processing. So we will have we'll have 24 plus 2 telescopes. Here, the MEU will process only the data coming from the 24 nominal normal telescopes. And inside these boxes, those boxes we will have 12 DPU boards that are being designed here in the Institute. In total, we have 2 MEU boxes, and that will connect with the ICU. The ICU is the system that finally send the data to Earth. Well, this is what we are doing here in the Institute, in the audit, a box with plenty of electronics inside. The last budget that we have is that this box will have about 9, we will weight about 9 kilos and will with a consumption of 77 watts. This is a general scheme of the electronics that we are developing here. So just to mention, this is the MEU PSU with the different DPUs that will process all the data coming from the cameras that are illustrated here. And once all the information is processed, is sent to the ICU, well, ICU through the routers, and the ICU will be responsible to send the data to Earth. And this is a scheme of the DPU. And this is one of the guys working in the audit. Most of you know him, with a breadboard of the DPU. It is an elegant breadboard. That means it is the final size will be is a 1:1 scale. So what I wanted to say. Well, these are more pictures of the prototypes we are working on now, just to test things. We are now in an early phase still, and this is a prototype of a motherboard in which all the different DPUs will be connected. And now, once I describe a little bit what we do from the point of view of the hardware, then the next 2 slides will be devoted to science, because we will not only construct the instrument, but we will do science. And apart from the core science in which the different teams, the different institutes are involved, in particular I will speak about the Granada team, which is composed from my team in the university and the team here in the institute, led by Rafa Garrido. And these are the main objectives that we are addressing right now related to the preparation of the Plato mission. The main objectives are those ones: to properly analyze the time series coming from the ultra-precise data. We are doing this from the launch of Corot because we detected some particularities, let's say, that could only be visible from these very high precision light curves. And we are working on it, and we have made some advances. We want to constrain the physical processes occurring in the stellar interiors. That is, we are, well, our expertise is mainly stellar, so we are using all this data to advance in the knowledge of stellar interiors, because we are doing astroseismology. So as I said before, we want to concentrate the stellar processes occurring in the stellar interiors. To do this, we will use not only astroseismic information, but other complementary information from spectroscopy and even well, radial velocities time series analysis. We are now working on developing 1D seismic diagnostic tools in order to connect with the current development of 2D stellar models. Why 2D stellar models? Because we are working with such a high precision that we are able to, let's say, be sensitive to the deformation of the stars due to rotation. Now we are starting to see the effects of the rotations in the stellar interiors with a kind of reliability. And the information coming from astroseismology is, thanks to photometric, ultra-precise photometric data, is so important for us, is so productive that we are able, through the analysis of patterns, to start to constrain the effect of rotation in stellar interiors. That is how rotation and how rotation modify the transport of elements in the stellar interiors, and how the angular momentum is transported, the energy is transported, how it affects to convection. For example, convection is one of the let's say key points in the stellar interiors, and that we need to constrain more, and together with rotation. And finally, we want to improve the stellar models of AF stars, intermediate mass AF stars, that is a little bit higher, more massive than the Sun, from 1 point solar masses to 3 solar masses, in preparation for the complementary science of the Plato mission. And I mentioned here this could be the jackpot, because these kind of stars will provide key information not only for these stars. AF stars are generally rapid rotators. Solar-like stars, in some cases we find some rapid rotators, and but generally, like the Sun, are not so rapid rotators. But in any case, the information coming from the AF star science, it will be key to understand any kind of objects. So that's what I say, this would be the jackpot, because not being the main core program, we will be able to provide an extra information that will, let's say, be fantastic for the mission and for the scientific community. And some years ago, 2 years ago, we start another line, an emergent line, what I call it, related to my Ramon y Cajal contract, which is the study of the dynamics, of planetary dynamics. The point is, once we have the stellar, the planetary systems characterized very well with these percentages in masses, radii, and ages, we will be able to constrain the condition that we need, the input parameters that we need to really constrain the dynamics of planets. And that's the idea. We are considering the planetary system as a whole, and with this we are studying in particular the close planets, including tidal effects. So we have finished to include tidal effects in one of our codes, and we are having quite promising results about this. And of course, this line could be one of the possible connections between stellar science and the Carmenet scientific objectives. Well, these are plenty of things that we are doing now. Different papers we are publishing in the last 2-3 years, but this is too much for today. Another day will come just to speak about science, but just to comment to 2 results that we have obtained recently. One in last year, another one in 2015, is that we are able to getting mean densities and gravities of AF stars. This is something which is quite important for the field, because up to now we had a kind of degeneracy in the astroseismic modeling, because we couldn't be able to constrain very well all the stars, because they are rotating stars. The astroseismic analysis is quite hard, because astroseismic modes are deformed by rotation and so on. But thanks to Corot and Kepler data, we have performed different studies in which we have been able to find a relation between one pattern found in the oscillation spectrum and the mean densities. So this puts AF stars, intermediate mass stars, in the same level of accuracy of solar-like stars. And thanks to this, we worked from 2015 up to last year. We worked in hard of this, and thanks to this information, we could be able to provide an estimate of the surface gravities of those stars only from only analyzing patterns in the oscillation spectrum. Analyzing patterns in the oscillation spectrum means that we are not relying too much on models. I said too much, but because we are always relying on models, but not too much of them. This is a comparison between gravities obtained with astroseismology and gravities found with spectroscopic measurements, right? And we found a very good agreement between them, and this means that only from astroseismology we will be able to determine with very high accuracy, even with more precision than in most cases than from spectroscopy, because spectroscopy, as you know, spectroscopy of rotating stars have large uncertainties, let's say. But this is not the case for astroseismology, and in most of the cases we have even lower error bars in the determination of surface gravities. This is important because now we are working on determining such surface gravity for thousands of stars observed by Corot and Kepler missions. We will do the same with the data coming from TESS. Of course, we will do the same with the Plato data. And that's it. Thank you very much for your attention.
Okay. Do you have any question for Juan Carlos? If you don't, I have at least one. Okay, I will start then. Thank you for the talk. We are looking ahead, 8 years ahead for Plato launch. I suppose preparation preparation observations will start soon. I don't know when, but they should start at some point. Then there will be also observations simultaneously with the mission, and then the follow-up afterwards. Well, follow-up as I understood as observations together simultaneously with the mission and afterward. Can you give us how you understand these preparation observations and follow-up for Plato from the ground?
Well, from my point of view, as I mentioned during the talk, the ground-based observations are key. So this is so important that the mission cannot just that the mission has to take this into account very seriously, and it does. It does, but the problem is that in some cases it depends on the discussions being held with ESO and other observatories in order to guarantee somehow the follow-up observations, because as I mentioned, we need the telescopes between 1 and 4 meters. In some cases, we have a lot of follow-up, and this is not easy. So we need some kind of guarantee, and this guarantee need to be discussed prior to starting the observations. And right now, the PI and the responsibles of the follow-up segment are just in this. But very soon, as they mentioned 1 year ago in the scientific conference of Plato in Birmingham, that probably in 1-2 years we'll have agreements, this kind of agreements with ESO and other instruments, so we will see the light. Afterwards, I'm not sure. I don't think that it is still, they are still in there. They're just guaranteeing that we have a proper follow-up.
Yeah. Thanks for your talk. Could you please identify others, other telescopes than 3.5 with Carmenes with for follow-up in related to our institute, if they are possibly used for making some kind of follow-up or not, please?
Well, I'm not sure. In fact, since we need high-resolution spectroscopy in order to perform radial velocities of time series and study the fundamental parameters, there are not too much telescopes able to do this properly, in the sense having the instruments to do that. I am thinking about La Palma HARPS, North La Palma, or even HARPS, but related to the Institute is maybe Carmenes. The OSN can play an important role, maybe not for the core program, but for the complementary science, but because with the photometer, even the photometer with the 90 centimeters telescope, we have very high precision photometric data in Strömgren colors, and this is something that that everyone understands that this is important, because it gives us color information for the astroseismology, and color information in astroseismology is very important to disentangle oscillation modes and to do astroseismology. So OSN can play another important role in the Platomation, Kepler, and TESS, and so on. But it's very difficult to put these small telescopes in agreements. I guess that for agreements they are searching for big instruments or I don't know, maybe competitive observatories that can be able to make such an agreement. But related to the institute, I see Carmenes for any kind of stars, but also for low mass stars, because we have the infrared too.
Juan Carlos, for this nice talk. I have a question about the possibility to measure the stellar age with astroseismology. Right. This is valid for any kind of spectral type, or is only limited to some special window of the spectral types?
Are provided for the core program, which is solar-like stars. From F, G, K, these kind of stars. We have demonstrated with Kepler observation that we are able to do this. For the other type of stars, there are different, let's say, problems to address in order to do astroseismology. For example, AF stars, they are rapidly rotating. So far, we couldn't find patterns. Now, thanks to the work of our group here in the institute and in the university, we are finding patterns that are able to give us mean densities and gravities. but we have not yet enough information to calibrate, for example, the impact on the precision of stellar ages. But we are working on it, trying to gathering a good sample of stars observed by Kepler and Corot now, and we are working on we have just prepared a sample also that will be observed by TESS. And with this, all this information and using machine learning that we have just published last year, we will be able to at least start to see if we will also be able to achieve such a precision for intermediate mass stars.
Okay. So if there are no other questions, we thank again our speaker. And that's it.